Hello everyone, this is Terry Erzman. I'm the Chief Marketing Officer for Percona. Welcome to today's webinar. Before we get started, can you please raise your hand in the GoToWebinar control panel if you can hear me all right? Okay, see lots of hands up. Thanks everyone. We will be recording today's webinar, and we'll send out a link to the recording as well as a copy, a downloadable copy of the slides later today or early tomorrow. Within the next 24 hours, you will receive an email to that link. If you have any questions during the webinar, please enter those into the questions panel in the GoToWebinar control screen, and we'll answer as many of those as we can at the end. If we have extras, we'll pass those along to today's speakers to write blogs in answer to any unanswered questions. All right, with that, I'm pleased to introduce our two speakers for today. So first, today will be Peter Zaitsev, who is the CEO of Percona and also a co-founder of the company. And our second speaker is Robert Hodges, who is the CEO of Continuent. And Robert has over 3 decades of experience in databases and distributed systems, and he's the original designer of Continuent's Tungsten software. He's also the main committer, or one of the main committers on Tungsten Replicator, and has implemented numerous features including parallel and multi-master replication. So we'll start off with Peter and hand it off to Robert in a little bit. Peter, off to you.
Thanks, Terry. So I will start by briefly mentioning the background of Percona. We started essentially as a consulting company in 2006 with our big goal of making the businesses successful with MySQL. Over time, we have found that that's not enough just to provide consulting, helping people to optimize the queries, set up proper architectures and the indexes. And we found what we also need to make software which runs those systems better. And this is how we engaged into developing our own software. So our software at Percona was essentially created with this very focused need to resolve the real application problems which is so in the field at that point in time. And obviously we wanted to have that ready to use by the most demanding enterprise applications, websites, and so on and so forth. We also made sure our software is compatible because many of our customers were running MySQL, and so they didn't want to take any significant risks upgrading to something which may be not comparable. So we tried for as much compatibility with Percona Server as possible. And finally, all the software we distribute, and what is going to be mentioned from Percona side of this presentation is open source on RGB license. The Percona Server, that is their most well-known piece of Percona software, which is our drop-in replacement for MySQL Server. Our goal with this software was essentially to help people to achieve better performance and reliability. And we have done a lot of code changes to achieve that. We also provide a very agile support for Percona Server with our support agreements with quick resolution of bugs and problems. We have a development team in-house which is very agile and able to resolve those problems very quickly if they arise. In terms of performance standpoint, we have generally better or equal performance compared to MySQL Server. A lot of our focus in the recent years was to the new technologies such as the systems with many cores as well as SSDs and solid-state drives. We also invested a lot of times to deal with problems which are often called stalls, dips, or bleeps. This is when a system has unstable performance if sometimes it stalls and doesn't perform very well, even if the average performance of that can be good. We found that's a very common challenge, and resolving that was very important. Finally, we focused a lot about the ability to achieve a better performance. We found that in a lot of cases the limitations are not really imposed by the MySQL server itself, but actually by ability for DBAs to be able to find what exactly is a bottleneck, what are the core queries which need to be tuned, indexes which needs to be added or removed, or configuration options which need to be adjusted. And we implemented a lot of features in Percona Server to assist those. Here is one of the graphs I wanted to share, and this actually goes towards the showing both a better performance and a lot more consistent performance with Percona Server compared to MySQL on some very high performance flash graphs. You can see the graph, which is a blue one for Percona Server, is almost a straight line, while MySQL has a lot of dips of slow performance from time to time when there are some background housekeeping activities performed. This is another example of a small but very valuable improvement a lot of DBAs would appreciate. If you are running production system, you know you often have to change your structure by adding their columns to your structure, database structure, or dropping the columns. And in Percona Server, we have extended the alter table functionality with, which can be enabled by this expand fast and extraction option, which can really improve performance of those named operations many times. I've seen cases that's 10 times or more, which can really help you to implement the changes in production, minimizing downtime. Another important change, example of important change which a lot of DBAs appreciate, is ability to reach a peak performance quickly. Because as we get with larger scale systems these days with more and more RAMs, those systems perform very well, but also it takes longer and longer time for them to achieve a peak performance, because it takes a lot of time to bring the cache from the disk to the cache. That especially applies if you're running in the environments like the cloud, which often has not very fast storage, or if you don't simply use flash. Sometimes it may be measured to hours. And we have implemented a feature in Percona Server which allows you to store their information about the buffer pool context in a special file and restart very quickly. As you can see with this graph, we essentially, with Warmup, are able to reach their good performance in minutes instead of an hour or so in this given case. I also mentioned a lot of benefits come from the transparency, right, on understanding what exactly is happening in the server. And one of the most used features in Percona Server is information about the used tables. We allow a very simple way to understand what tables your application is using, and so what tables have to be reviewed in terms of indexes or maybe pruned, archived, or something like that. That's a very helpful feature which is available in Percona Server very easily. Another feature which we work a lot in our consulting practice is the additional information in the slow query log, which is just described here. As you can see, we provide a lot of information about what exactly query was happening, wherever it required temporary tables or temporary tables on disk, wherever it had full table scan or required a file sort. A lot of those really help us to understand what queries are causing performance problems and what queries help us to optimize that. This slow query log is integrated very nicely with another piece of Percona software called Percona Toolkit, and we can analyze those queries with PT Query Digest tool to get all kind of reports. I'm just describing one example here, which is called Profile Report, right, which shows us what exactly queries are taking the most response time, so the queries which will be the most important candidates for for optimizations, to begin optimization with. The other very well-known component of Percona Software suite is Percona Xtrabackup, which is essentially a very humble tool which helps you to back up and restore your database. But it just does that well. It supports all kind of storage engines, but it is very much focused on the InnoDB and XtraDB storage engines. That is a physical level backup, which makes it very efficient in terms of both backup and restore. It's designed having as little as possible overhead in mind, so you can keep your production running with limited impact, because we have discovered a lot of customers actually have a lot of problems in production because of their backups. The backups can be slowing their systems down dramatically, and we focused a lot about avoiding that. We support backup from sale, slave or master, and we really have a lot of support for large databases, such as having an incremental backup, so your backups can take, subsequent backups can take only a fraction of space compared to the full backup. We can do a backup for multiple tables in parallel, as well as compress and encrypt backups, which can be important. What is also very important in this tool is it can be managed by just DBA on its own. It doesn't require any special storage configuration. It doesn't require you to have a SAN with snapshot compatibility, or even a Linux with LVM snapshot. Even if you're a DBA who doesn't have a full access to the system but just MySQL user privileges, you can use this tool for the hot backup of your database. Let me now shift to the question of the challenges or increasing demands. We see what, as the time goes, the question of high availability with MySQL gains more and more importance. The first reason for that, as I believe, would be as MySQL is used for more and more high-value enterprise applications, as well as a lot of web applications using MySQL become very, big companies with very costly downtime, if it ever happens. Impact of the cloud is also important, because with the cloud we typically get more of smaller MySQL instances, as well as those instances are more prone to failures. And that means what we cannot just hope, but they will stay up, and we have to plan for failures. And not only plan for failures, but plan for a lot of failures, and hopefully find a way to automate handling those and make it easy to do that. Traditional technology for maintaining high availability with MySQL, which is the most popular in the field, is MySQL Replication. It's very mature and proven technology. It's rather easy to use. A lot of people know how to do it, but it also comes with a number of limitations. One of those is serialized execution. That means it's not parallel, it runs in a single thread, and that can be really causing a lot of bottlenecks. It also have limited filtering and data modification compatibility. So if you want something more complicated than replicate one master to the slave, then you may find the very limited features you have in there. And finally, it is hard to use slave efficiently. What I mean by that is MySQL replication is asynchronous, so it's possible that some data wouldn't be propagated to the slave right yet. That means that a lot of customers have to resolve to some very complicated applications functionality to find what kind of reads can be performed from the slaves and what can't, which is rather complicated, and there is no dedicated support out of the box to solve that problem in any way. And finally, it's hard to manage failover with MySQL replication. Again, out of the box, it doesn't provide you very good ways to manage that, where it requires a lot of manual steps to achieve that, and which was often very common cause of problems. And at this point, I wanted to mention that MySQL Continuent Tungsten is their software which you have been seeing a lot of customers using to really solve a lot of those problems and much more. And at this point, I want to pass it to Robert, who will tell you more about this.
Thank you very much, Peter. So let me go ahead and show my screen. Peter, can you confirm that the audio as well as that you can see my screen?
Yes, yeah, thank you. I can see the screen and hear you well.
Okay, great. Well, it's a real pleasure to be here today. I've known Peter for years. We've actually worked side by side in a number of cases with the Percona folks. So it is a great pleasure, as I say, to be here and do this webinar together. What I'm going to do is basically pick up exactly where Peter left off, and we're going to shift from looking at MySQL and sort of the basic infrastructure for storing your data as well as backing it up and restoring to what you need to layer on top in order to build industrial strength applications. So with that, I'd like to take a quick detour to introduce Continuent, much as Peter did for Percona. So we are the leading provider of clustering and replication for open source databases. And when we say open source databases, we really mean MySQL. We've been in this market for a number of years, have sort of followed the technology as it's steadily improved, and have a large number of deployed installations using this technology. Our product is Continuent Tungsten, as you've already heard, and it basically does two things. It does clustering, which is providing commercial or industrial strength high availability, as well as performance scaling and overall data management for MySQL. We also have replication. So you may have heard of the Tungsten Replicator. It's a pretty well-known open source replication product for MySQL. And these two things are tightly coupled because in order to build clusters, you must be able to construct replicas. For that, you need replication. We originally designed the replication to serve that purpose. It turns out, of course, that once you've built the clusters, the replication in turn can be very useful for moving data across sites, also as a way to get to other database types. In this talk, we'll be mostly focusing on the clustering capabilities. One other thing that I should say is we are optimized for use with Percona Server and Xtrabackup. These are both very, very popular builds of MySQL. Xtrabackup, I think, is almost certainly the most widely used backup for InnoDB. So because our customers use it, we've optimized Continuent products to use them as well. Just a little bit about facts. The clustering that we're going to be talking about today, the largest installation we have, which also happens to run Percona 5.5, processes something like 500 million transactions a day on Continuent clusters. They have up to 150 terabytes of data in MySQL. It's a very, very large installation. Tungsten Replicator itself was Application of the Year in 2011. I'm happy to say we shared that honor with Xtrabackup. We are pretty well known in the community for, as I say, for the clustering and replication, and we have around 80 customers currently deployed, and that number is growing quickly. Just a little bit about those customers. There are some household names. So, for example, Marketo is very, very well known for marketing automation, as is Constant Contact, F-Secure for security, Juniper Networks for a variety of products, other mobile folks. If you bought anything off Zappos in the last year, you've actually been using Tungsten software. We help Zappos capture, move purchase requests in real time from MySQL servers over to Oracle for fulfillment. And we've done a fair amount of work with Facebook as well. So these are some of the bigger users of MySQL actually on the planet. So this is software that's worked in very, very demanding environments, as does Percona. I'd like to now dive in and talk a little bit about how the clustering works. So Tungsten clusters, as I say, take off where Percona ends. So we take cluster, we take off-the-shelf open source databases and we combine them into clusters. And the way that we do that is, this is sort of a architecture picture, but you can basically think of it as involving 3 elements, which I'll show you in a little bit more detail. The first is we add replication. So we built our own master-slave replication with some special capabilities to make clustering work better. For example, we've supported global transaction IDs for years. The next thing is you need clusterware. So we have manager processes which are able to see a consistent view of all of the databases, understand what each one is doing, issue orders on them, and handle problems like failover. And then finally, we have an intermediate layer that we call connectors, which are basically proxies. They run in user land. They don't have any hardware dependencies. And they create the illusion that this cluster of off-the-shelf databases is a single database. So your applications actually don't know that they're talking to multiple servers. This is a very flexible architecture that handles some important problems, and these include fast failover. So for example, in master-slave architectures, if your master goes down, you need to get another one up in a hurry. That's a problem that we handle. Another very important problem is zero downtime maintenance. So being able to have a site which may do extended maintenance. Percona has obviously done some really great things to help shorten those time periods, but there are still times where you need to go offline, often for hours. We allow that to happen transparently. And finally, to be able to scale load efficiently. So individual databases may be fast, but you'd actually like to take advantage of the fact that you have replicas and automatically spread load onto them. And for most people, you want to be able to do this without changing your applications or data migration. And this is where the fit is very good with MySQL builds like Percona, because we basically treat the database as a black box, take advantage of all the capabilities that it has. As it improves in performance and in capabilities like monitoring, so does the system built on top of it with Tungsten. So returning to something that Peter said, a lot of people, when they first look at this, they say, well, doesn't replication do this already? And it's true. You can set up very large systems with simple MySQL replication, and many people have done it. In fact, many people on this call have probably done it. The problem is that replication doesn't do everything. There's a number of bad things that can happen. For example, if your master fails, how do you get another master pushed up and in service as quickly as possible so that you remain available to your customers? Another problem is, how do you deal with the fact that a slave is lagging too far behind? How do you make sure that applications, for example, do not use that slave to give it time to catch up and also not to return stale data? And then finally, this issue of how to maintain the database without stopping apps. This is critical. Most people that we work with no longer have maintenance windows because they run 24/7 operations. If they're down, it's actually measured, and they may have a few hours a year maximum that they can take real downtime. And in the meantime, they must be able to upgrade applications, upgrade hardware, do all kinds of changes without taking systems offline. So this is where the Tungsten architecture comes in. Basically what we do is we add software to the existing MySQL instances and turn it into a full-blown cluster. So this is not what your application sees, but I'm basically showing you some of the basic plumbing behind it so you can see how it works. In this particular cluster, DB1 is our master. We have 2 slaves, DB2 and DB3. We add replication, as I mentioned. That's the base of this architecture. We have the manager processes, one running on each node, and that's the thing that makes this a cluster. The managers use a special protocol called group communications so that they can all see each other and do reliable messaging so that they all have a common view of the state of all the databases. Moreover, one of those managers at any given time is the boss in the cluster. We call it the coordinator, and that manager is responsible for taking action, for example, for failover. Finally, the managers do something very important, which is that they supply information about the state of the cluster to the Tungsten connectors. Connectors can run anywhere in your data center. Actually, they can even run across data centers, as you'll see. Applications connect to them. As far as they're concerned, they're talking to a MySQL database. The connectors transparently route the SQL into an appropriate database based on what what the application needs to do. So for example, thanks to the information that's supplied by the managers, if somebody comes in, begins a transaction, we will automatically ensure that they are talking to a master, wherever that happens to be. The key thing about the connectors, as I think I already mentioned, is they don't depend on hardware, so they're particularly appropriate for environments like Amazon Cloud Infrastructure, where you can't use VIPs, and you also don't have hardware mechanisms that allow you to route traffic. So this is the basic architecture of the system. We call this a data service. Let me just show you a couple examples of how it works, and then we'll go over and actually demo it. So automatic failover in this type of system is fairly simple, at least from the perspective of applications. If you imagine you have an application that's talking through a connector to the master, let's say that the master fails. So what happens is the clustering software in Tungsten, that is to say the manager, will detect that the master has become non-responsive. This is actually kind of a tricky problem to know when something's non-responsive and when it's just slow, but we've found that typically if something doesn't answer the door to a TCP/IP connection, it's a pretty good sign that it's down. At that point, we halt master connections. So we'll automatically inform the Tungsten connectors, hey, this guy's going offline. He may be already dead, but we need to halt new connections so that your applications that are connecting in at this point will appear to hang. The next thing that we do is, because this is master-slave, we need to go look around the cluster and find the most advanced slave. So we'll pick a slave, and that will be our candidate for a master for any pending transactions that slave has received but not committed yet to be applied. Next, we'll go ahead and promote that to a full master, reconfigure the other slaves so that they talk to it, and re-enable the connections. At that point, your applications, which have briefly frozen, are going to now connect in. Now, one thing I should say is that if you have when you have a master crash like this, people that are applications that are in the midst of a transaction will see a broken connection. There's almost no way to avoid that, but anybody new coming in will be held, and of course the existing application processes, when they resubmit those transactions, they will automatically be directed to the new master. And then the final thing that you need to do after a failover is you need to go fix the master that failed. We don't do this automatically because usually when you have a failover, it's a good idea to go look and see exactly what happened to make sure that you understand what it was and that you're not just bringing something back online that's actually broken. So we have some simple commands to do the master recovery, and we'll show you those as well in a minute. So that's the basic cycle for automatic failover. Failover in general is something that we use rarely because MySQL systems, when they're in operation, are generally very reliable. What is a lot more common is to need to take downtime for maintenance, and this is based on very simple calculations. For a lot of people, this is 90% or more of their actual downtime on databases. So the neat thing about having this architecture with the connectors is you are able to take the slaves offline one at a time and do what we call a rolling upgrade. So for example, a standard process for this would be to go ahead and take one of the slaves offline, run your upgrade, and return it to the cluster. The nice thing about this is that upgrades, as you probably know, don't always go so great when you're actually in a production situation with production levels of data. So if the upgrade fails, you can just discard that slave and, for example, restore it from a backup. If it does go well, you can go ahead and repeat it for your other slaves. And then finally, when your slaves are done, you can go ahead and do a switch, which is where you promote one of those slaves to be master and then upgrade the old master. At that point, you're fully upgraded and you've taken no downtime. One final thing that I want to mention before we go into a demo is backups. I mentioned that we're integrated with Xtrabackup. It is a very, very good tool for, we particularly use it in situations where people are processing up to 1 terabyte of data. We're very interested in some of the parallel capabilities that should extend it beyond that. But we have built-in commands which will automatically run a backup also restore the backup and do what we call recovery. So recovery is where we try and make a failed master come back as a slave if we can. We have out-of-box support for Xtrabackup, which is actually going to be our default in our next release. We also support MySQL dump, but do not recommend it for anything other than small data sets. We have integration, which we do as an implementation exercise, so that you can also use file system snapshots, for example, on NetApp. Let me talk a little bit about connectivity, because I think this is one of the most interesting features of this architecture. So I mentioned we have these proxies that provide the indirection layer, and these, as I said, completely implement the MySQL wire protocol. We have a couple of very limited cases where we don't fully implement the protocol, but they rarely come up. In most cases, applications connect through the connector and they have absolutely no knowledge that they're not talking to MySQL. So they'll log in, for example, and what we do is we go ahead and initiate the connection using a JDBC driver. So for example, you would come in, ask for a connection, we'll initiate a connection on your behalf to the master. Once that's done, we use something that's called pass-through. So we don't actually do translation of the calls. We're just looking at the packets. If there's something interesting, we may take action, for example, switch it onto another connection. But in general, we then just act as a pass-through where a query coming in from the application goes straight into the target database server, and then the result sets come streaming back through the connector. So the overhead on this is quite low. I've rarely seen it exceed any, more than 2 or 3%, and that's because in real MySQL applications there tends to be a lot of data, so most of the time is actually spent fetching it and operating on it in the database. There is a very interesting capability of this connector that Peter alluded to, and that's what we call read-write splitting. So read-write splitting is the idea that as a query comes in, we have a look at it, and if appropriate, we'll dispatch it to a slave. There's 3 general ways you can do this. A lot of applications like Drupal 7, for example, are already slave-enabled. In that case, Tungsten can find the slaves for you. It can automatically come back to the master, and it can take care of making sure you don't get a slave that's too far behind. There's another policy, which is called read-write splitting. In this case, we just route any auto-commit read to a slave. This is actually kind of nice for media apps, which tend to use it. They are not too concerned about reading what they wrote. Finally, there's a feature called Smart Scale, where writers can see their own writes, but we actually load balance the reads. This is a very common protocol that's used in sites like Facebook. It's sometimes called session load balancing, so I'd like to show you how it works. The basic idea is that if you have Smart Scale enabled, when your write comes in, we'll send it to the master. And the way we know it's a write is that it's either a statement like insert, run as auto-commit, or we see begin. In that case, we're going to route it to the master. And we're also going to make a note of what the position of the bin log was when you wrote it. So then if a read comes in, we're going to look at that read, and then we're going to go find out where the slaves are. And if the slaves have not yet processed that write, we're only going to read from the master. So we're basically going to hold you on the master for the duration of that session until that read reaches the slave. And then finally, when it actually reads, when the slave has actually replayed it and is up to date for that session, then we would route potentially route that read over to the slave. If no slaves are available, we read from the master. So this is a very powerful capability that even on highly performant MySQL servers can give you excellent performance improvements, and it also uses your hardware very efficiently. So with that, you have sort of the basic idea of how Tungsten works. I'd like to switch over and do a quick demo. And in this demo, I'm going to start by actually installing Tungsten on top of a couple of Percona 5.5 servers. Let me just show you the command that I'm running. So it's going to be highlighted. I'm going to create a cluster, and this command has, in general, about as many options as MySQL uses when it starts up. I have a few more here because I'm actually working in a lab environment and I have some special configuration. So this is the command I'm going to run. It's called tpm, and it's actually going to install the cluster software on top of these MySQL instances. So let's go ahead and run the command, and then we'll talk a little bit about what it's doing while it runs. So off it goes. What it's going to do now is we're running from a single host. I have two hosts. One is called Logos1, that's going to be my master. Another one is called Logos2, that's my slave. I have bin logs enabled on both of these, so they're both set up to do replication. And what the installation is doing right now is it's going out and doing a bunch of checks. And for example, if you see my screen refresh, we look at my.cnf values, and if we see things that we're not sure about, so for example, setting the flush interval or other settings for InnoDB, we'll give you a warning, or if we see things that will lead to a failed installation, we'll stop you right there. Generally speaking, if your system has the configuration, the prerequisites set up correctly, we will go ahead, push the software out, completely configure it, and bring up the cluster. And that's exactly what's happened here. So let's just jump in and have a quick look at this cluster that we've created. So we'll go in using a little client called cctrl, cluster control. And when you're in cluster control, there's a command called ls that shows you the state of the cluster. So what we see in this cluster is there are two data sources. They're called Logos1 and Logos2. Logos1 is the master. It's online. Logos2 is the slave. It's online as well. We also have a couple of connectors in this which are connected, but nobody's actually using it. So one other thing I should point out, the coordinator up above is the name of the manager. That's the host that's actually the boss in this cluster. And we show that this cluster is in automatic mode, which means that it will fail over automatically if a manager goes down. So at this point, what I'd like to do is just prove that this cluster is alive. So let's do something called cluster heartbeat. And this sends a heartbeat event through. And what we see is that if we refresh, we see that the Logos1 master, its progress has gone to the global transaction ID. The Logos2 slave has also gone to 1. So this is alive. We can also flip the master and slave very easily. So we'll do switch, for example. And what this will do is actually flip the master and slave, demote the old master, promote the slave. And it's as simple as that. On an unloaded system, it's very quick. And I can switch them back. And we will, and back they go. So the very simple management commands. Now, what I'd like to do is, I don't know for sure if the master and the slave are completely synchronized. So what I'm going to do is go ahead and run an extra backup to back up the master, and we're going to restore it on the slave. And while that's happening, we're going to go over and look at the connectivity. So off it goes. It's running an extra backup in the background. And what I'm going to do in the meantime is I'm actually going to log into this through the connectors. So if you look over on the right side, I have a couple of windows. In the bottom window, I'm connecting through MySQL. So here we have the MySQL application, and this is just the ordinary client. You'll notice I'm using a different port, 9999. That's actually connecting through to a connector. When you look at it, it looks as if as far as you can tell, we're actually connecting to the to Percona 5.5, but you'll notice the word tungsten inside the server label. That's the only way that you can tell that you're actually talking through a proxy. There is another way, which is you can actually ask. We have a special command so you can see who you're really talking to underneath. So let's ask the proxy who we're talking to, and we're talking to Logos2. So that means that this is routing us to a slave because it thinks we may be getting ready to do reads. Let's go ahead and do a read. So for example, we'll do a show variables like hostname, and here we go. We see the host name is Logos2. That's where the connection is open to. Let me show you something interesting. I'm going to begin a transaction. I'll go ahead and type begin. This starts a transaction. Let me run the same command. So if you look at it, you'll notice I've now switched to Logos1. So underneath the covers, the connector has actually switched us over to to the master because it knows that it's looking at the transactions or the packets as they go by, and it knows we started a transaction. Finally, I can ask the connector, where are we talking to? Here we go. And sure enough, the connector is now open to the master. So I can go ahead and commit this transaction. So that basically illustrates this transparent connectivity that your application is sitting up on top of this connectivity layer, and we are transparently bouncing between databases. Let's make this a little interesting and stick some load on this system. So let's go ahead and start a program to generate a little load. So we have a little program called Evaluator. It's just going to it does about 50, well, when it's fired up, it does about 50 or 100 updates a second. I think this one is a bit slow, but it's now updated, and we're putting load on the system. If we come back and look at the cluster, what we'll see is that we have we basically have the Logos 1 and Logos 2. Master is online. Progress is 563. The slave is also online and is receiving updates as well. Let me go ahead and do a switch. So I'm going to go ahead and switch between the master and the slave. And if you watch the screen over on the upper right-hand side, what you're going to see, oh, interesting, okay. Looks like we had a long query there. Generally speaking, you see this dip down to 0. It looks like we had a transaction that was taking a little bit longer than expected. So it was actually terminated by the connectivity layer. But you see a dip here where we go to 0. Basically, everything stops, and then what happens is as soon as the switch is done, it basically allows the transactions to go through again. And Peter alluded to the difficulty of managing this type of failover. What we actually do is we stop the transactions. We basically allow the connections to drain out. One did not, so we cut it off. And then what we do is those are handled at the client side. Once we believe that everything has stopped, we'll actually do a purge command underneath where we'll kill connections to the database. We will go ahead and kill any remaining connections so that there's no possibility of them committing after we failover. And then finally, we'll send a transaction through to ensure the slave is up to date. So this allows you to move from a master to a slave with no possibility of data loss. So one final thing I'd like to do is I'd like to go ahead and just kill this new master that we have. And I can do this from within the within CCTRL, but people always think that we're maybe doing something sneaky. So I'm just going to go to the command line on Logos 2, and I'm going to kill MySQL. Just going to issue a stop. You'll see up above that you'll see that we lose the connections because MySQL just died. You'll also see that there's a period of time where we have 0 updates, but then we quickly resume as the application retries its connections. And if we go over to the CCTRL and look at the state of the cluster, we see Logos 2 is shunned. It's failed over to Logos 1. That's why it was shunned. So it's kicked out of the cluster. It cannot be used until we do something to fix it. And I'll do that right now. So I'm going to say data source Logos 2 recover. Oops. We're going to try and make it a slave. And if it's not damaged, doesn't have extra transactions or anything like that, it'll just come back. And this sometimes works. The replication is asynchronous, so every now and then we have a few transactions that get trapped. We're not putting a lot of load on this system, so in fact it was fully caught up, and the transactions were loaded. What we could do, though, if that were not possible and we needed to get it back from a backup, we would just do the following, where we would say restore, data source Logos 2 restore, and we would basically run a restore, and this would begin to pull things back from that backup. So that's basically how you restore a system. So with that, the demo is done. Let me just switch back to our slides, and we have a couple of things to before we get to the end. So that was the demo. So one thing I should mention in passing is that Tungsten does DR sites as well. And we have webinars where we talk about this in more depth, but very simply, we can automatically set up not just local clusters, but clusters that span sites. This is great for the cloud. We actually use it ourselves. We not only cluster across Amazon regions. We actually cluster between Amazon and Rackspace. All our IT is actually out on Amazon at this time, with backups on Rackspace. And the connectivity knows how to connect across them. This is actually kind of a nice feature, particularly if you do metropolitan clusters where you have low latency between them. So with that, if you want to get Tungsten, you can come to Continuent, where the clustering is closed source. Full documentation is available on the website. Do come over and have a look at it. Contact us to get a download. You can, if you're just an open source person and want to go to bare metal. Advanced MySQL Replication through Tungsten Replicator is available on code.google.com. Feel free to download it and try that out. So with that, we're basically at the end, and I just want to say that as we've tried to show you in this talk, between the capabilities of speed as well as reliable data management on Percona Server with Xtrabackup plus Tungsten, you get industrial strength systems. So we sit on top of the Percona servers using the backups, Xtrabackup using server, enable 24/7 access, and also improve your resource utilization. And in fact, for our biggest customers, if you ask them why they bought Tungsten, it is fast failover, zero downtime maintenance, and this SQL load balancing, which improves performance as well as improves the resource utilization. One final thing, we're doing this webinar side by side. We have a number of common customers, so we're very comfortable, I think, on both sides working together. It's, I think, a pretty good match of the Percona software with their support, which is really excellent, and plus the Tungsten on top of that and with our own support, which I think is pretty good. So with that, Terry, I'd like to thank you and Peter for putting this webinar together and turn it back to you.
Okay, very good. Thank you, Robert. Again, just to remind everyone, if you have questions, please submit them through the questions input area on your GoToWebinar control panel. Looks like we have a number of questions. The first few look like they're directed to you, Robert. So first one is, what is the time frame on automatic failover and a reconfigure? Seconds, minutes? Does it matter how large the cluster is?
It's seconds, and it really depends on how you fail. So if it's just what I did, which is a crash, you basically would, if I kill my SQL, as soon as I look at it over in the cluster already knows there's been a failover. It will take, as you saw, a few seconds for your applications to reconnect. The longer case is if you have a failover because a host went down. In that case, we start a timer. It by default runs for about 60 seconds, and then we download, and then we fail over at that time. For planned failover, the biggest component of how long it takes is whether you have long-running transactions. We can optionally allow you to set that out to some, like a value like 5 minutes, in which case you wait for them to get done before you fail over. That's
Okay. Next question is, how does Tungsten prevent the split brain problem due to, for example, intermittent issues where we end up with multiple masters?
Okay, there's a number. Yeah, that's a really good question. The split brain is a big problem in any distributed system, and so we have a number of checks against it. So a big one that we have is that when a master does fail over, it stays down. So we shun it. I think you saw that in the demo, and we don't let it back until an administrator actually looks at it. So once they're failed over and down, they are not able to come back. The second thing we do is called witness hosts, so that this was actually in the configuration that I ran, where we set a couple of well-known IP addresses as witnesses, for example, a DNS server. And if guys get isolated, they have a protocol that they go through to try and figure out if they are the only one left, or if perhaps they've just lost network connectivity. In the latter case, they go down again to prevent a multiple master. Finally, we have automated rules where we basically shut the cluster down if we see multiple masters. We just stop operating.
Okay, very good. Next question. What is the minimal number of nodes in a Tungsten cluster if used for load balancing?
2. So really, I think the most, it's kind of interesting that MySQL has become so capable that the largest number of nodes is about 4 that we see with customers. 2 is the minimum number. I think that the usually what drives this is actually not load balancing so much, but HA. I like 3 because it allows you to have one node down for maintenance, another one available for failover, another one available as your master. Beyond that, usually when people need more than 5, 6, 7, 8 nodes, they tend to actually have sharded their data and put it in separate clusters.
Okay, very good. And this next one, I'm not sure if Peter or Robert would like to address. The question is, how many routers, connectors, should be running in a typical web server environment? Is one router per web server too many?
I'll take that one. No, it's not. It really depends. We've done tests where we've run it up to 75 or more routers. When you actually, and I assume these are the tungsten connectors we're talking about as opposed to a hardware router. So you can run it up to dozens. Actually, when you get to that level, because the connector is written in Java, it's often better to put it on its own host with a load balancer in front of it, or its own hosts, and minimize the number of places you have to install Java.
Okay. Next question. We have many databases and tables that are MyISAM for reason of read speed and copyability to multiple places. Would this work with a heterogeneous engine cluster, or does it need to be all InnoDB, DBs, or databases and tables?
I think this is one for both me and Peter. I'll just jump in and say we prefer InnoDB and we strongly recommend it, but we understand people have reasons for staying there, so we do support it. Peter, do you have thoughts on? I'm sure you guys have thoughts on MyISAM versus InnoDB as well.
Yeah. I would say that's indeed. MyISAM niche is getting smaller and smaller with each MySQL release, right? And I think the biggest piece of MySQL was strong. Their full text search is going away with MySQL 5.6, where it's been added for InnoDB storage engines. There is some niche use where MySQL may make sense, but that's really rare.
Okay, next question. If a master server loses power and a slave takes over as master, do we have to restore the old master from a database backup, or can it catch up from the replication logs?
It depends on, okay, so that's an interesting question. It really depends on whether the master had extra transactions. So our replication is asynchronous. We're big believers in that for a number of reasons that have to do with its reliability and robustness. But the problem that you get is that when a master goes down, you may have a small number of transactions that are trapped there. So typically what you'll do is you'll bring it back up. It's fairly straightforward with Tungsten to figure out which transactions were lost. You either decide whether you want to keep them, tell your users, or ignore them. And then at that point, you can go ahead and repair the master, typically by restoring a backup. There are other ways to do it, and I think that actually one of the more interesting ways that people do this recovery, because sometimes backups take a long time to load, is if you have very large data sets, use file system snapshots.
Okay, very good. I think a related question, what is done in Tungsten to ensure master and slaves don't get out of sync, like what can occur using traditional MySQL replication?
Well, there's a number of things. One is we test the daylights out of it. We do have CRCs on the logs, so some of the basic problems that you sometimes see in MySQL don't exist. We are fully crash safe. This is actually one of the places where things tend to get a little mixed up. So as long as, particularly if you're using InnoDB, our slaves are 100% crash safe because we commit into InnoDB, and then we store also in InnoDB our, as part of that transaction, our commit point. We also have a consistency checking that you can run inside the cluster. I didn't illustrate it, but you can just run an automatic consistency check on tables, those are sort of the basic. There are, I mean, to be sure, there are ways that clusters can get out of sync. I would say the most common reason is that people accidentally write to the slave. That's really hard to avoid. So we strongly recommend that people shift away from the 3306 and instead use a different port number and only let the connectors use 3306. That prevents user accidents.
Okay, very good. Next question. Does your clustering introduce any constraints on schemas or SQL statements? For example, foreign keys?
None. It's plain old MySQL, and I think this is really one of the strengths of this architecture. That, as I said at the beginning, we're huge MySQL fans. We really, really like the database, and I think that one of the things that's great about it is how much it's improving thanks to the efforts of Percona as well as everybody else in the MySQL community. So it's basically a pass-through. We do no magic on the SQL.
Okay. Relay question. In the case of a transaction failure experienced by an app, does the app get error notification of the reason? For example, kill versus fail versus trapped?
Interesting. That's an interesting question. We do have some slightly different error codes in the case of a failover, but in general, we just try and pass back whatever MySQL provides. The one case where we have to pass back an error message is if we kill a connection as part of a failure. You actually saw that as part of the demo. So we try to be pretty transparent and avoid, in a sense, creating new behavior for your applications.
Okay. This is a nice link to the Percona Live conferences, which I'll mention, and you see on Robert's slide currently. Percona Live London is next Monday and Tuesday, and Percona Live MySQL Conference and Expo is in April of 2013 in Santa Clara. But there's a question specifically about Percona Live London, and it is, will your multi-master, multi-site MySQL databases made easy with Continuent Tungsten speech in London be similar to this webinar or different?
No, it'll be quite different, actually. We'll be talking about real multi-master, and I think that there's going to be, if you're going to that conference, I would definitely, I think you're in for a good time because we'll be talking about asynchronous multi-master, particularly across sites. Percona is going to be talking about synchronous multi-master, so I think you'll get a full panoply of some very interesting approaches to this problem, and in our case, we'll be focused on doing things like maintaining payment gateways, things across sites, and work over WAN.
Okay, very good. Next question. What happens if the TCP ping fails but the database is okay?
We fail over. So that's the cost. What we found over time, and Peter, has thoughts on this that he's published, and I think have been widely read. We have found that on balance, that's the best way to determine whether something is down. It's pretty, and what we're really saying is, can the MySQL server just accept a TCP/IP connection? It doesn't have to be, do a select one or anything like that. It's just selecting it. So there's still a possibility of a false failover, but we found that in practice it's pretty rare.
Okay, and a question about Tungsten Connector. If there is any kind of is there any kind of failover for the Tungsten Connector if it fails?
Yes. So there's a couple of options. One is that it's we have a watchdog that automatically runs. It's called something called the Java Service Wrapper, and if the Tungsten Connector becomes unresponsive or actually fails, it automatically restarts it. So when you're running on an app server, that's that can occasionally happen. It's pretty rare. The other thing that you can do is, if that is a strong concern, I would put the connectors behind a load balancer, for example, HA proxy, and then at that point, if a connector drops out, your load balancing will shift you to another one.
Okay, and then final question. This is maybe one for both you and Peter. How different is this configuration from just the Percona XtraDB cluster with HA proxy?
Well, I think that, yeah, that's, I'll give my answer and then Peter can give his. So one of the things that we're looking at is we're basically trying to solve a bigger problem, which is building a full-scale system with the ability to have the backups automatically incorporated, as you saw, with the ability to do zero downtime maintenance without actually having to do any special, using very, very simple commands to switch turn things online and offline, and then also to have this intelligent load balancing. Another thing which I think goes to the question that came up before is that we're also very focused on being able to distribute data. So you got just a taste of it with the DR clustering. That's a feature that is actually very popular. And then of course there's multi-master clustering for things like online games as well as payment gateways. So we're basically focused on solving some of the problems that are necessary to build complete systems. Peter, if you want to contrast on your side.
Yeah, thanks, Robert. Well, I think one of the biggest things here is obviously the replication being synchronous, right? And asynchronous, which do have a different applications between each other. And I think that's the different form of packaging and integration. That's another very big piece I would mention. Another thing, what you kind of alluded briefly in your presentation here is if you look at the Percona Xtrabackup cluster, it's mainly focused on the complete replication in MySQL only. There is no, partial replication or data changing intended, while Continuent has a lot of support for those options as well as getting the data replicated to the different database system, right? I think you mentioned in your presentation you have replicating data from MySQL to Oracle, right? And I know we have connectors to all kind of other different data stores, which Percona Xtrabackup cluster doesn't have.
Yeah, exactly. And as I said at the beginning, we use MySQL as a black box. As it gets better, we take advantage of those features. There may come a point where the XtraDB cluster actually is, it's evolved enough that, hey, maybe Tungsten should just sit on top of that. So that's something we're looking at with a great deal of interest.
Okay, well, thanks everyone for attending today's webinar. Just to wrap it up again, Percona Live London is next Monday and Tuesday. If you're in Europe and you'd like to attend and you haven't registered yet, please do so immediately. The hotel's very nearly full. There's just a few rooms left. We do have sponsors with discount codes for the event. If you can't find any of those, feel free to email me. I can give you a discount code. That'll save you a bit off the conference passes. And all of us will be there next week, so hopefully stop by and speak with us. And again, I will pass out the questions to Robert and Peter so they can blog to these other questions that we didn't get to. Sorry we didn't have time for everyone. And we will send out a link to a recording of the webinar as well as to the slides within the next 24 hours. And with that, thank you, Robert and Peter, and everyone have a good day.
Yeah,
Thank you. Bye-bye.
Bye.